Great. So we're very happy to have, for the third talk in the afternoon of the third day, Daniel Berwick-Evans from the University of Illinois, who is going to tell us about how do field theories detect the torsion in topological modular forms. Dan?
Great. Well, thank you. It's been really fun being here, seeing some old friends, making some new ones. It's yeah, thanks to Hisham and Urs for putting this on. So the context of the talk is going to be this conjecture of Siegel and Stolz-Teichner that relates kind of two very sophisticated objects. One is topological modular forms. This is this theory of Gors-Hopkins. Let's see. Does this need to stay awake? Maybe that's the problem. Okay, I'll just have to like touch it from time to time. Anyway, so this theory of TMF from Gors-Hopkins and Miller, and then by Lurie. What's that? You can say never. Yeah, I thought I had, but let's see. Well, yeah, maybe this maybe we'll delay us more than just me being attentive to the iPad. So anyway, so we have this theory of TMF that really kind of was born in the 90s out of some work really coming from physics initially and then going into homotopy theory. It's this very sophisticated object constructed from homotopy theoretic methods. And then Siegel and then later Stolz and Teichner started to describe this geometric model based on ideas of Witten that's supposed to give some understanding of TMF in terms of the geometry of manifolds. So I mean, geometry is kind of different depending on who you ask, but by geometric, this really is something about global analysis, differential geometry, manifolds. So this will be the context. I'm going to try to explain a bunch of the words over here. There's kind of a ton of stuff over there. I'm not going to describe as much over here, but this is like equally complicated, unfortunately. But my hope is that I can give you a sense of what's here and also start to tell you about some progress. So let me just mention a few reasons why this is sort of surprising / interesting. So this gadget over here, TMF, if you just plug in a point, you get a ring. And this ring is similar to modular forms, but not the same. And the big difference is that it has a bunch of torsion. And this torsion is kind of surprisingly complicated. It knows a lot about the homotopy groups of spheres. So maybe spheres aren't your thing, but they are a very useful yardstick in homotopy theory to say like how good your invariant is. You have an invariant, how many homotopy groups of spheres does it compute? And TMF does a very good job. So it's something that's deep and important in homotopy theory for that reason. But when you're faced with this conjecture here about relating field theories in TMF, it's sort of shocking that field theories could possibly know about all this torsion. I mean, that just seems like too good to be true almost. However, if it were true, what this is telling you is that there's some very interesting space of field theories over here that's sophisticated enough to know about all this torsion, and that makes this a very good proving ground for testing out different definitions of field theory. Okay, so that's the preamble. Let me just kind of mention the goals for where we're headed here. So I want to tell you, as I mentioned, about these different adjectives about field theories that show up on the Stolz-Teichner side of the story, and use this to both motivate the conjecture and also explain some of the ingredients. And then the main result is going to be a kind of one categorical approximation to the result that doesn't give TMF, but it gives some approximation to it. And in particular, it gives this partial answer to the title question that we get some TMF torsion out of this description, interpreted in terms of field theories. So I want to tell you, at least for a few of those classes, like this one new that Domenico talked about the other day, the Z-mod 24, where that comes from in supersymmetric field theories. Okay, so the unfortunate thing with this topic is that like the objects I'm not going to be able to describe them in detail, which makes me uncomfortable and probably makes you more uncomfortable. But are there any questions so far just about the kind of the landscape of the problem? You're willing to come along for the ride? Okay. All right, so I'm going to start with talking about geometric field theories of different flavors. This has a lot of resonance with what Dimitri was talking about earlier, and sort of the motivations are very much the same, trying to understand these spaces of geometric field theories. There are some subtle differences, but I don't think we'll notice most of those today, so a lot of what Dimitri says is just going to carry over directly. I want to start with kind of maybe more examples. So I want to talk first about quantum mechanics. And quantum mechanics as a one-dimensional Riemannian field theory. So quantum mechanics, we'll kind of boil it down in a few moments here to the ingredients that you probably know and have seen. But to start, let me just talk about Riemannian Bordisms. So here are some pictures that come out of the Riemannian Bordism category. It has a pair of objects. There's a point with the positive and a point with the negative orientation. This blue and red dot. And then I'm always going to read my morphisms from bottom to top, so time goes up. And our Bordisms look a lot like they do in just the ordinary 1D topological Bordism category, except they have a length, which is just a positive number. So you have a lot of the same pictures that you have in 1D TFT, but you have to keep track of this length parameter. So for example, when you glue two intervals together, this in topological field theory is just identity composed with identity is identity, but here they're actually different morphisms that you have T and S goes to S plus T. And then this thing that shows up in dualizability, this picture here, in TFTs no longer does, precisely because this thing here is no longer the identity. It's some morphism that depends on a length. Okay, so a lot of the things that you know about 1D TFTs are going to carry over, but you have to remember lengths are involved. So maybe one thing to point out that's useful is that, and this is another thing that distinguishes it from the topological Bordism category, is that there's this semigroup R greater than 0 that keeps track of how intervals glue, and that gives you this subcategory of intervals of the Riemannian Bordism category. So whenever you have a functor out of the 1D Riemannian Bordism category, you can restrict to the semigroup, and you're just going to get a semigroup representation, which is time evolution in quantum mechanics. Okay, any questions on those pictures so far? Good. So let's now start spelling out when I take a functor from this Bordism category to vector spaces, what happens. So first I get the value on the plus point. That will be my space of states. I'm always going to be assuming reflection positive, so like Dan talked about, Dan Grady. I won't say that much about it, but these orange arrows kind of indicate the types of things that are special about reflection positivity in this setting. So for the other point, I'm just going to get the conjugate of my space of states, for example. That's one consequence, or one of the pieces of data, in fact, of reflection positivity. Okay, so we have our spaces of states. We also have this time evolution. So remember that when I glue together intervals, I get some semigroup representation. Well, that means that there's some generator of that representation, which is our Hamiltonian. And when you compose these things together, you're going to see the gluing of intervals, right? So for the other Bordisms, I'll just mention briefly the types of things you get. When you look at Bordism from 2 points to the empty set of length t, that's going to be like the pairing between two vectors, but with your time evolution smashed between the bracket notation here. And it's important for this to make sense that our H was self-adjoint, or else it depends on which side I put this time evolution, for example. And also another consequence of this reflection positivity, this is actually an inner product, not just a pairing. And another Bordism that's important is if I look at these closed Bordisms, these circles, I just end up seeing traces of time evolution. So in contrast to topological theories where you just get a number, a single number, here you get a function that depends on the size, and that's the partition function. So this depends on this R greater than 0 parameter, the length. Yeah.
So we always have the other way around?
Yes. Yeah, the other way around is allowed, and it basically is what it does is impose a trace class condition. We can talk about it after. There is some kind of shadow of dualizability that's showing up here that's forcing certain properties to happen, and this particular one, and how it composes. That wasn't long enough to go to sleep, was it? How it composes with the other one, that's going to be something about a trace class property for like why this makes sense. Yeah, so it's important, but I'm going to kind of push that under the rug for now. So one observation to make is that if you have a 0 Hamiltonian, this all is going to be the data of a topological field theory. So that's the usual statement that topological theories have no dynamics. Hamiltonian is 0. But that also means that if you look at the ground states for one of these Riemannian theories, you'll get a topological theory. So inside of every one of these Riemannian theories sits a little topological theory. And sometimes that's an interesting topological theory. We'll see some examples of that shortly. Okay, so here's the example that perhaps you've been waiting for. If I take a manifold, a smooth manifold, oriented, compact, I can study quantum mechanics on it. I get my space of states being, I'm going to take C infinity functions. If you really want to take L2, we can still be friends, but I'm going to prefer Fouché for various reasons that maybe we can talk about afterwards if you care about such things. And then time evolution is this exponentiation of the Laplacian. And the inner product is the usual inner product integration with respect to the volume form. So this data that I've given here supplies kind of what you needed to fill in those pictures up above. Now, I mentioned at the beginning, these spaces of field theories are in some sense what is most interesting for that conjecture. And one kind of frowny-faced thing about Riemannian theories is that they form a contractible space. So there's like not enough rigidity for there to be interesting topology. You can just kind of deform wherever you want, and those deformations aren't interesting. So the first thing that you could do to make this more interesting is start to include symmetry. This is basically what happens in a lot of these condensed matter type theories. So I could consider some algebra A, and rather than just a bare Hilbert space, look at A modules. And it turns out that setup, provided that A commutes with a Hamiltonian, so acts through symmetries, that's going to be the same as a natural transformation. This takes some spelling out, and it's a fun exercise, but just maybe believe me for now that if you look at a natural transformation between the constant functor to just C in algebra is viewed as an algebra, and then there's some functor coming from A, and A is a bimodule, this natural transformation is precisely going to be this type of situation. So that's one way in which you can enrich the story here is through symmetries. And Stiltz and Teichner call this a twisted theory. Fried and Telemann call this a relative theory. There are other names for it in the literature. It's sort of something that comes up from a variety of angles depending on kind of what you care about, but it's a natural notion. And one example you might take is if I have, say, a finite group acting on a manifold by isometries, then I get the group ring acting on functions, and that's going to commute with the Hamiltonian and give this type of situation here. Okay, questions so far? Good. All right, so now I want to add supersymmetry. This is like kind of, I think there are 7 parts of geometric field theories that I'm going to do as we kind of build towards these two-dimensional super Euclidean blah, blah, blah. So adding supersymmetry, I first want to describe the examples because I think they really convey why supersymmetry is interesting mathematically, and then I'll come back to the Borzum category description. So the first example of supersymmetry in math, or the first example from physics, I suppose, that mathematicians latch onto was this one that Witten gave about Morse theory and supersymmetry in, I think, is that 85 or 86, something like that? 82, 83, oh, okay, even earlier. So this one has n equals 2 supersymmetry. I'll explain what that means in a minute. But it's basically the same setup as we had in quantum mechanics, but you take differential forms rather than functions. And okay, you still have the Hodge-Laplacian, that's your time evolution operator. This will be a Z2 graded vector space, just the mod 2 grading of forms. And that'll be important in a second. Because what we want to do is, with this Hamiltonian, consider some odd square roots. So if you take Q1 being this thing here, d plus d star, you take Q2 being I times d minus d star, both of these will square to your Hodge-Laplacian, and they commute with each other. And that's one of these examples of a superalgebra. So this is n equals 2 because there's 1, 2 odd square roots, and they commute. Now, the thing that is more interesting from the point of view of topology is now when you look at the ground states, before when you looked at ground states, I didn't mention it because it's not that interesting, you see constant functions. Here you actually see the entire cohomology of M, de Rham cohomology, because you get the harmonic forms. And so by Hodge theory, that gives you much more information about the topology of M. The partition function in particular tells you about the Euler characteristic. And in fact, if you analyze, I mean, this is in particular constant in T, right? The Euler characteristic won't depend on that T. And if you analyze the limits of this as T goes to 0 infinity, you can recover the Schern-Gauss-Bonnet theorem. So in this example from n equals 2 supersymmetric mechanics, you get a rich amount of differential topology and geometry of manifolds. It's a very nice example. And there's more to this story that I'm not telling about Morse theory as well. So this like just keeps giving. So there's another example that's perhaps more indicative of the things I'll talk about for the rest of the talk, which is n equals 1. And this involves spin structure, so it's maybe a little less familiar than the previous example. But nevertheless, if we have a manifold with spin structure, which gives you a bunch of stuff, principal spin bundle, a spinor bundle, and a Dirac operator, you can form a supersymmetric quantum mechanical system out of that. So in this case, the Hilbert space of states will be the spinors, and the Hamiltonian is the Dirac-Laplacian, the square of the Dirac operator. And because we define it as the square of something, well, it definitely has an odd square root. But there's usually only one. And so this is just n equals 1 supersymmetry. In this case, the ground states also have meaning in terms of topology. This was this Clifford linear Dirac operator. So by the Atiyah-Shapiro construction, its kernel is some Clifford module. And when viewed as a class in K-theory, you're getting exactly the index. And similarly to before, if you look at this partition function, it's going to be constant in T. It's going to, in fact, be equal to the index, and you get, well, equal to the rationalization of the index. And you get in these limits, as T goes to 0 and infinity, the two sides of the Atiyah-Singer index theorem. So this is another example where, starting with kind of supersymmetric quantum mechanics and physics, we get a lot of rich mathematics. So I'll talk a little bit about how this is interpreted in terms of Bordisms. And then the goal will be to replace one-dimensional Bordisms with two-dimensional ones. And that's going to lead to kind of where we're headed. Are there questions on the examples first? These are somehow the key motivation for what comes next. Wait. All right, so back to Bordisms. I'll describe how you can look at this n equals 1 version of supersymmetric mechanics. So this will be kind of the general version. We'll talk about the spin manifold version in a second. But in terms of one of these natural transformations again. So in this case, the algebra that's going to be relevant is this Clifford algebra. And I'm going to get a natural transformation. But what I really need to tell you about is this Bordism category. So this is the 1/1-dimensional super Euclidean Bordism category. Bit of a mouthful, but the first good news is that the objects are just the same as the usual Riemannian Bordism category. Nothing there changes. They get called superpoint, but there's just still two of them. So that's no different. What does change is our notion of length. So before we had this parameter t that was telling you the length of an interval. And now you have this even parameter t, but there's also this odd parameter theta. And that's what keeps track of these super Bordisms. So it's the same pictures as before, but the things that decorate them are different. So the jump from one-dimensional TFTs to one-dimensional Riemannian field theories, this is just another jump where it's all about how you label your pictures more than kind of what pictures you're allowed to draw. And the crucial thing is how these things compose. And they compose using this sort of funky multiplication. So you can take 2 points in this R11. And when they multiply, there's like this kind of Heisenberg-y style cross term that shows up. Because theta and eta, these are like the odd parameters in your length, because they anti-commute, this ends up being a non-commutative supergroup. So in context, when you think about lengths, usually you're not thinking about non-commutative things for one manifolds, but that's sort of the thing that makes these one-dimensional super Euclidean manifolds interesting, is this non-commutativity. But this is there for a good reason. The point is that you want the Lie algebra of this group to mimic the structures we saw before. So there should be a single odd operator that squares to your Hamiltonian. In the classical setting, that would be that you want an odd operator whose square is time evolution. And this Lie algebra is the thing that comes out of this Lie group structure. And that's why it's baked into the notion of geometry here. Okay? This is all like this part of supergeometry that I'm trying to kind of minimize as much as possible, but there's a lot more to say about how to make this rigorous in terms of supermanifolds. All right, so let's look at our example again. So I'll just tell you what happens on the plus point, with the minus point being the conjugate. It's the space of states, no surprise there. What happens on these intervals of length t theta? Well, that's this expression here. So when you spell this out, you end up with a homomorphism from this now super semigroup into Clifford linear endomorphisms on your state space. And so rather than the time evolution we had before of just being the semigroup R greater than 0, it's this non-commutative super semigroup that shows up as time translation. And you can draw the other pictures basically by wherever before you saw e to the minus t Laplacian, just put in this thing instead, and it's all the same. All right, so the next thing I want to add in is this manifold X that was at the very beginning. These were two-dimensional field theories over a manifold X. So I want to emphasize that X and M have nothing to do with each other. M was like the target space that we did quantum mechanics on. X is like a family parameter for a family of quantum mechanical theories, and they don't talk to each other, at least not initially. Okay, so what you do to consider these quantum mechanical theories over X is you just take all the Bordisms and you map them into X. So rather than like a bare point, you have a point in X. Rather than a bare path, you have a path that is a path in X, and appropriate super words in places. And then once you have that Bordism category, you can then do the thing we were doing before, is just take functors out of it valued in vector spaces, the usual functorial field theory story. And out of one of these functors, rather than getting a single odd operator Q acting on some state space, you get a bundle of state spaces over X and a family of odd operators. And when your theory is nice enough, there's an index that you can take, and that lands in the KO of X. So the question of being nice enough is something to do with ellipticity of operators. There's a condition on the field theory to have that happen. And it looks in physics a lot like this existence of low energy cutoffs, but that vary smoothly in families. So there's a technical thing to say there. It actually ends up working out quite beautifully how the ideas in physics communicate with the index theory, but just want to flag that. One other thing I want to flag for later is that, in fact, this thing that extracts a K-theory class doesn't really depend on arbitrary Bordisms in X. It really only depends on the ones that are close to the constants. So close to constants meaning that in this world of supergeometry, you can talk about maps that are constant up to nilpotent elements, kind of similar to tricks you can play in algebraic geometry. And that's the only part of the Bordism category that actually participates in this index here. So there's, it looks like this is some huge category, like you've got infinite dimensional mapping spaces, but in fact, this index only depends on a finite dimensional subcategory. That's one way of saying it. Okay, so we've talked about Riemannian field theories in 1D, supersymmetry in 1D, field theories over X. And now I want to move the dimension up by 1. And then we'll add supersymmetry and over X and all of that kind of in pieces afterwards. So what is a two-dimensional Euclidean field theory? That's the new ingredient. So Euclidean here will be taken in the sense of Thurston, which is flat Riemannian. That sort of doesn't match with the terminology in the physics literature, but I think we're stuck with this. The other important ingredient here is that the boundaries of these flat Euclidean manifolds are geodesic. So what's a bit curious is that on the one hand, two-dimensional Euclidean field theories are harder than two-dimensional TFTs because you have this there's a metric involved that makes things more complicated. On the other hand, they're easier because you don't have anything other than tori, basically, for example, in closed genus, and you don't have anything other than cylinders. So like the pictures are actually quite restricted that you're allowed to draw, but they do carry these labels by geometric parameters. So here are some of the pictures that you can get. So what I've drawn over here is the upper half plane with some point tau, and then when you quotient out by some action by L that's translating to the right, you get a cylinder. And that cylinder has, well, okay, there's an inner, like a circumference of the circle, that's this L, parameter L. And then you also have parameterizations of the boundaries that are basically determined by this tau. So altogether, we're gonna end up with a moduli of objects in this two-dimensional Euclidean Bordism category given by circles of varying sizes. Those will be the geodesic boundaries, disjoint unions of these as well. And then the morphisms are pretty much going to be given by cylinders and tori, where you have to read the cylinders in different ways. So you can read this as a Bordism from circle to circle, or a pair of circles to empty, or from empty to a pair of circles. But that's really it up to disjoint union for what you see. So in some ways, it's not as rich as the TFT story, and in some ways, it's more rich. It's kind of this funny thing. And then another thing to point out is that when you glue cylinders together, if you think about stacking these things on top of each other, you're just going to be adding the parameters tau. So it's a different semigroup. It was r greater than 0 before. Now it's the upper half plane and the complex numbers. But again, it's just going to be some simple kind of representation of a semigroup that you get in the end. All right, so now when we think about writing down a functor from this Euclidean Bourdesum category to vector spaces, there were just these two objects that I mentioned, and then reflection positivity will mean that we only really care about one of them. But, well, sorry, there are two one-parameter families of objects depending on the size of the circle, but we only care about one of those families. So we get these state spaces for each size of circle, and those are parametrized by this L. And so really you think of like a smooth family of state spaces over r greater than 0. That's the way to think about this. And in particular, because it's smooth, they're all isomorphic, but maybe not canonically. And for each of those circles, you get one of these semigroups coming from your cylinders, so you're going to get some action by the half plane. And the standard notation for these sorts of actions is you have these Q's to the L0 and L0 bars. This is kind of a piece of what you get in conformal field theory. We don't get any more L's because it's Euclidean, not conformal, so this is it, just LL0s. And the way that the Q's interact with the half plane is this exponential formula. So when you start composing these, you'll get the addition of tau corresponding to composition. And then reflection positivity will also force these things to be self-adjoint, just like we had in the case of quantum mechanics. So the important thing that happens in 2D theory that's really, I think the magic, is what happens when you take traces. So in 1D, when you took a trace, you get a value on a circle, and circles don't have that many interesting automorphisms. However, tori do. There's this mapping class group action by SL2Z, and when you take a trace, you interpret this, either physically using the path integral or in terms of Bourdesum categories as gluing your cylinder into a torus. So you interpret this as the value on the torus, and then this thing on the right has to have invariance properties under this SL2Z action, which means this thing on the left did too. And that's, in a nutshell, kind of the magic of 2D field theories and why they kind of have taken over a bunch of math, is that modular forms are kind of lurking in the background. We'll see that a bit more clearly in a minute. Okay, any questions on the 2D Euclidean case first? Okay.
Maybe a quick one.
Yeah.
Do you have any explicit example of such?
Yes. So yeah, excellent question. I almost put them in, but they're like, some of them feel a bit hollow to me. Given any modular form, I can cook up one of these things. And it's sort of dumb. It's like for each coefficient of the integral modular form, you take a vector space of that dimension, and then you use that to cook up an action by this thing. So for any integral modular form, you get one of these. Again, that's not, like, because of this property, that tells you that's in fact all of them. But it doesn't feel like a very satisfying construction to me.
And an example coming from like an action function or something.
So there, then you can do things like free fermions, similar to what Conrad was talking about. Those examples have some complication that doesn't exactly fit into this framework, having to do with certain anomalies. But nevertheless, they can be made to fit with those sorts of caveats. I'll mention, there's another one, yeah.
Sorry, shouldn't every two-dimensional CFT give an example?
Yeah. So the issue here is that invariance would be a modular function, not a modular form yet. So the CFT would have to have central charge 0, and there aren't so many of those. So yeah, we need to do some things to make things a little fancier, and then all these examples will be there. For this particular case, it's just like, this is shockingly rigid. That's it's an incredibly strong thing to try to place on these theories, it turns out. And that has to do, in one way or another, with the theory of modular forms. There just aren't that many modular functions in the world. I'll give some examples later that are not quite, less stupid than this, but yeah. Sorry.
It's related to super.
Yeah, the examples I'll give will have supersymmetry. Yeah. Okay, so supersymmetry. So I want to start kind of as before with the basic algebraic data of supersymmetry and then backtrack to what that means for the Bourdesums. So if you have these operators L0 and L0 bar, you can ask for odd square roots of either one of them. And maybe you've seen like n equals 2 comma 2 or n equals 1 comma 1 or n equals 0 comma 2. The number comma number is the number of odd square roots of this one and the number of odd square roots of that one. So I'm going to be most interested in 0 comma 1 supersymmetry, which means that there's just one odd square root of the L0 bar. And that's usually called G0 bar. And that's it. You can look at more supersymmetry. Certainly, there are lots of reasons to do that. But for the purposes of the results later, this is the example I want. So then in terms of Bordism categories, we're going to be looking at these field theories again as representations. And I need to tell you what this Bordism category looks like. So as before, the objects are just the same as in the Euclidean case. Kind of made super, but like the moduli of them is identical. So there's really nothing that changes there, but what changes are the Bordisms, the morphisms in the Bordism category. And it's roughly analogous to what happened in quantum mechanics, that it's the labels of these Bordisms that change, that rather than just being labeled by a tau, you have this triple where, I mean, implicitly before we also had a tau bar. I'll mention in a minute why I'm going to distinguish tau and tau bar. But then the important thing is there's this odd thing theta that's also showing up. So the moduli of these Bordisms has some odd directions in it. And then when you compose, when you glue cylinders together, you get this interesting group structure where, just as before, there was this funny cross term that shows up between the products of your odd variables. Now notice this is just on one of the two chiralities of C, and that's why it's this chiral supersymmetry. It's just in the anti-holomorphic direction. If we had put it on the other side, then rather than 0 comma 1 supersymmetry, it'd be 1 comma 0. If we did things on both sides, anyway. So you see, so there's some kind of handedness to this composition rule that shows up, and in particular, that gives you this non-commutative supergroup. All right, so now the modularity, like sort of the important property that happened before was that when you look at the trace of the value on a cylinder, that's now this thing. That was SL2Z invariant. The thing that happens now that's new is because you have this odd square root G0 bar, in fact, using kind of this McKean-Singer argument, but in a slightly different context, the Q bar dependence drops out. So being independent of Q bar is another name for holomorphic. And what you end up with is the value on a torus, which is this trace, is some power series in Q. And it's a power series that reads off indices of these odd operators acting on certain kind of S1 weight spaces. Okay, so there's some algebra here, but the upshot of all of this is that rather than just being an SL2Z invariant smooth function on the moduli of tori, it's actually an integral modular form now when you look at this partition function. So we've achieved via supersymmetry some holomorphy, which it's important to note that there was nothing holomorphic about the original theory. Chiral supersymmetry is very different from like chiral conformal or holomorphic field theories. So supersymmetry is able to get you these sort of holomorphic quantities without putting holomorphy into the Bordisms from the beginning. Okay. Any questions about that? All right, so continuing on this trail through geometric field theories, there's this degree thing that showed up in the original conjecture. And this is related to what Conrad told us about these free fermions, or the degree n twist, or there are various names for it. But roughly speaking, it's like the Clifford algebra of the loop space of something. It's this big algebra. And you want to consider state spaces that are modules for that. What I'm talking about today is actually a pretty significant simplification of what Conrad has been up to, in the sense that like his setup is much more sophisticated than what I need here. This is just this like type 1 factor in his world, whereas the type 3-1 factor is the important part. So this is related, but it's somehow not yet using the full depth of what Conrad has done. Okay, so in this setup where you have these theories that are twisted or modules over this algebra, however you want to think about it, then rather than getting just this integral modular function from before, you get a modular form. So this is where weight is coming from, is by allowing this degree n aspect.
And
Yeah.
so what is n? I mean, I can see that n on the right-hand side is the cohomology degree.
Yes.
And becomes the weights.
Yes.
On the left-hand side, what is n?
It's like the number of fermions that you have interacting with the theory, like acting on the theory.
Oh, I see. That's
Yeah, yeah. So it's this. There's n's in places maybe. Okay, so there's degree. There's an n here. There's an n here. There's an n right there. All the same n. Yeah. So yeah, good question. It's the generalization of Clifford n that shows up in K theory though. So Clifford n, there's a kind of a maybe overcomplicated way of Clifford algebras is some kind of odd Heisenbergy thing, and it's the generalization of that. Yeah, well, okay, so yeah, I haven't really said specifically what anything is in terms of it's these internal categories. So it's the internal Morita bicategory, yeah. Yeah, drat. Okay, so yeah, so let me give an example now that I think is it? Please, yeah. May I be agnostic about some of these words? I mean, one answer is yes, another answer is maybe not. We can talk about after. The distinction between anomaly, symmetry, free fermions, they're all related, definitely. And from one point of view, definitely, there's an anomaly. I mean, one way to say this, perhaps, that makes it unambiguous is if the partition function is a modular form of some weight, that means it's a section of a line bundle, not a function. And that's the hallmark of an anomalous theory. Yeah, it's encoded right there. So the value on tori in the cobordism category gives the line bundle. So one way of saying it is that over the moduli of tori, you have to write down a line bundle, and the line bundle you choose is the one whose sections are modular forms. No, so that's all coming through basically this functor. So this is the usual boards. Yeah, I think I see what you're saying because the way that Siegel set things up is slightly different here. It does have a flavor of projective representation theory that's going on, but it's basically like asking for kind of representations valued in modules rather than a central extension acting on a vector space. So it's a different way of saying the same information. Here, the modules are these modules over fair n. Yeah, so right, there are several ways of packaging this, and this is the way that Stoltz and Teichner have set it up. But I fully believe that one could do it in terms of an extension instead, and it would work the same way. I don't, off the top of my head, know how that translation would go, though. Okay, so next, there's this example that I think is the one that really kind of began everything here. So if you start with the string manifolds, this is a spin manifold where this fractional Pontryagin class also vanishes. Then you can form one of these field theories in this sense here. So what you do is you take a space of states that looks like this section of some big tensor product of, or maybe direct sum in Q, depending on how you set all this up, of spinor bundles. So this sim Q to the K is just keeping track of some S1 actions as you take symmetric powers. Roughly speaking, this is coming from taking the tangent space of the loop space, restricting to the constant loops and choosing a polarization. That's where this would show up. And then the G0 bar that you'll take is this twisted Dirac operator. The action by L0 is encoded by this Q in a way that's not completely explicit, but I could tell you about it with formulas at some point if you'd like to see. So this Q is telling you how L0 acts. G0 bar squared is L0 bar. So altogether, this is telling you a representation of these cylinders, this Q to the L0, Q to the L0 bar plus theta G0 bar. And then if you take the trace of that representation, you end up with this index of G0 bar that we have looked at briefly before as some Q expansion. And this is how Witten originally constructed the Witten genus. I'm being a little bit fast and loose about the role of fermions in here. Roughly what the secret is that this algebra is Morita equivalent to the ordinary Clifford algebra. And that's allowing me to kind of move some things around. Okay, any questions on the example? So this is the last kind of last ingredient about geometric field theories that I'll need, which is this over X aspect. And that is just mapping everything into X and taking now functors out of this category that aren't just bare circles and boardisms, but ones that live with the map to X. And this is this category of 2-1 Euclidean field theories that Stoltz and Teichner talk about. There's two things that I'm adding to it in addition to their definition. One is this reflection positivity. This is important for kind of self-jointness of operators, things like that. And then also this low energy cutoff, which is some kind of ellipticity condition, which is going to allow me to write down these indices and families. So those are both technical things. They're important, but maybe we won't get into them now. Right, so with this definition, you can then start to write down some maps to some cohomology theories through ways that I've mentioned, kind of, or at least alluded to. One is if you take the index of this G0 bar operator, you get now, rather than just a Q expansion of numbers, you get a Q expansion in K-theory classes. And then rather than a single modular form as the value on the torus, you get cohomology with values in modular forms as the value on tori. And by the same magic as before, these things have to be compatible as cohomology classes down in here. So that is to say, the value on a torus, if you run around here, you take your cohomology class values in modular forms, you Q expand, or you take some index in K-theory, you take the Chern character, those have to be the same. And that's the expression that the trace on a cylinder is the value on a torus, same as before. But you get better than inequality of classes. What you get is actually homotopy compatibility data between the underlying cocycles here. So these field theories are giving you more than just cohomology classes. They're giving you, for example, a de Rham representative here, and actually a map to the K-theory spectrum there. And those classes are homotopic down here. And this is, I did not expect this. I thought everything was broken and that life was miserable and this conjecture was false because I couldn't find the homotopy here that I needed, and basically forced the issue down to one computation of the computation and found the homotopy. So it's not something that I have like some snappy reason for why this homotopy exists. You compute it and it's there. I'd like to have a deeper reason, but I don't. It's something subtle about the moduli space of super tori that, yeah, apart from computing, I don't know how to explain it.
Sorry, could you say where the homotopy takes place?
Yeah, so it's down in here. I'll write down, so I'm about to have this thing called homotopical interlude, so I'll tell you much more about the homotopy theory. But in terms of field theories, it's that you have the value on the cylinder and you take a trace. That gives you one function on some moduli space, which turns out to be a differential form with values in these power series. You evaluate on tori and you Q expand. And basically having to do with how the index construction works, these things are not equal. There was some choices involved in both cases, and those choices are parameterized by something, and that's where you see a homotopy.
Right, but so you use this diagram of spectra.
Yes.
So on the bottom right is some Eilenberg relay spectrum?
Yeah, it's coming momentarily. Yes, definitely, yeah. So yeah, here's the diagram that it was once. Yeah, so I'm gonna call this homotopy pullback in spectra, KOMF. The players before that we saw were the spectrum KO with power series in Q, which is otherwise known as elliptic cohomology of the Tate curve, Eilenberg-MacLane spectrum for cohomology with values in modular forms over C, and then Q expansion on coefficients lands you here, and the Chern character lands you there. So just for these three legs of the diagram, you can take a pullback and you get some cohomology theory, just defined as the homotopy pullback in spectra, and that's that thing. We'll come back to that fellow in a minute, but first note that TMF maps to these places, and there's a homotopy coherence. This is just of how TMF is built, is that if you have elliptic curves, you get maps out of TMF. This map up here comes from evaluation of the Tate curve. That's called the Miller character. This map here comes evaluating on the rational moduli stack of elliptic curves. And you know that because there's some isomorphisms between curves that in fact everything is homotopy coherent, and that gives you a map from TMF into this pullback. So using the string orientation of TMF, you get a string orientation of this pullback as well, just by composition. Now you can also form a string orientation of this pullback by like just writing down something to KO, writing down something to ordinary cohomology, and producing some homotopy. This is just something you can do using analysis and differential forms and kind of good old classic geometry. That gives you a second string orientation of KOMF. And there's a theorem that they are the same. And this theorem verifies a conjecture of Bunke-Naumann, these invariants, related to these invariants that Domenico was telling us the other day. And their results plus this index theorem give you stuff. So some of these are just their results on the nose. So they show that the map from TMF to KOMF on in degrees 4k minus 1 injects on 3 torsion. They also show that you get this injection in degree 3. And then they also show that they build their string Boltzmann invariant in one way, and then this description up above in terms of some map of spectra gives another way. And they're the same, so you have these different descriptions of what happens in different degrees. So for example, in degrees 4k, if I have a 4k dimensional string manifold, and I look at what happens under this invariant, I get just the Witten genus as an integral modular form, the classic construction from 86, 87. But if you look in degrees 4k minus 1, you get some torsion invariant. And it's the torsion variant that looks at exactly these sorts of classes. Okay, any questions on the homotopy stuff? I know that spectra is sort of, they're not everyone's friend. All right, so back to field theories. Using the reasoning I mentioned before about not only do there exist some maps to some cohomology theories, but some homotopy coherence, you get a map from 2-1 Euclidean field theories of degree n over x to this cohomology theory from the pullback KOMF of x. And this, this is sort of approximating Stiltson-Teichner's conjecture because KOMF approximates TMF. The approximation can be stated a bit more sharply because, in fact, this map doesn't use everything about the category of field theories. It only uses some part of the category of field theories. So it's constructed, this arrow is constructed by mapping to some piece of a field theory and then applying some co-cycle construction. So in fact, you know that the class that you're getting in KOMF only depends on basically the values of, from the diagram from before, it just depends on the values on cylinders and tori. So there's more to a field theory than just that. In particular, I guess I've been putting this under the rug for a little while, but I'll mention it now, that the cylinders and tori are just in this Ramon sector. So it's really only like half of the data of a field theory that's showing up here. And then it's not fully extended, and there's other things that aren't here either. So you can approximate this category of field theories by this category with the lowercase field theories, and then you have what is very close to being an equivalence. I can say some words about that, but this is almost like an isomorphism when you take deformation classes. There's a small issue, but it's sort of an issue that's already there in K-theory, so it's hard to make it go away. Okay, so then when you are given a string manifold, you can try to construct an object in this smaller approximation category to field theories. And you win. You get an object that encodes exactly these values that were in that Witten genus construction with some new ingredients that have to do with these torsion invariants. And the field theory you show actually agrees with what the string orientation gives you. So you start with a string manifold, you produce a field theory, or you take your co-Boltzmann class of string manifold and get some cohomology class, and those are the same. So in particular, when so Hopkins and Mahowald proved this theorem that when you look at the lowercase version of TMF, that pi star of m string surjects onto that by the string orientation. So what that means is that all these torsion classes are actually detected by string cobordism. And so in particular, field theories are detecting all the torsion in the image of this map. So that's using these results of Bunke-Naumann, all the 3 torsion degrees 4k minus 1, this Z mod 24 in degree 3, and some other spurious classes here and there. And so then just to reiterate, for these 4k minus 1 dimensional string manifolds, you get torsion invariants. If you look at what shows up in the argument up above for producing the class here, so you look at this composition here, you'll exactly recover what some physicists did. Well, I don't know what Theo is these days, but anyway, people who argued at least using physical reasoning about some torsion invariant, you recover exactly their argument for the torsion invariant that you get out of this machine. So it gives a rigorous derivation of their torsion invariant of field theories, and again, communicates with Bunke-Naumann invariants, communicates with some of these TMF torsion classes. And so in particular, when you're looking at the sigma model with target S3, which is SU2, to define a string manifold from that, you need to choose a degree 3 class, which is otherwise known as a level. And that's enough to get you one of these field theories I mentioned, supersymmetric, well, partially defined supersymmetric sigma model. And then this level K mod 24 turns out to be the invariant that you get in the torsion of TMF. So in this extremely nice example, the torsion is very easy to describe. You just take the level mod 24. Okay, thanks.
Any questions for Dan? Me too.
So Dan, I was trying to follow everything. At no point did you actually show us how you construct this EFT to one, or did you?
Well, I alluded to it. Let me try to say a bit more. So up here, the key information for producing a map into the pullback here was the value on cylinders and the value on tori. And this lowercase EFT is just those values. And it's in fact those values on maps to X that factor through nilpotent. So it's these two finite dimensional moduli spaces.
So I'm asking even something even more basic. Even the uppercase EFT, you're just sort of positing the existence of that.
So that was defined, I hope. Yeah, up, let's see. Well, okay, it's in here. Oh, and I think with X and there's actually, yeah, here we go. There it is, right there.
So there exists a spectrum called.
This is a category. For each n, you get a category.
And what do you do to that category?
You take isomorphism classes to get a set.
Okay.
And that set maps to some cohomology group viewed as a set.
So when you talk about these spectra arguments, you're going to have some enhancement, right?
Well, it depends a bit on what one means. I mean, in the end of the day, all the cohomology groups are just groups. They're sets. And to map into a set, okay, yes, you do need to map into some points of some spectrum and things like that. That uses the categorical structure. But the map in the end factors through isomorphism classes.
You were mentioning earlier you found a homotopy.
Yes.
So you were talking about topological spaces.
So the homotopy is like a piece of a differential, like it's a literal differential form data that shows up in this category. So it's not like there exists a homotopy. It's here's the differential form that actually mediates between these two de Rham cohomology classes. Or, you know, the closed differential forms that give you the same de Rham cohomology class. Right. And those de Rham cohomology classes are exactly the things down here. So you have this equality. And this is some equality of differential forms that you build out of these sorts of things. But then you get a bit better than just, sorry, it's an equality of de Rham cohomology classes that you get. But then you get a bit better that, in fact, these differ by a specified exact form.
So is there an obstruction to creating a spectrum? Or?
So there's suspension isomorphisms that you need to build, basically. That's the missing piece.
I see.
I have an idea for how that goes, but I haven't written things down. Yeah, it's again tied into this free fermion story, in fact. So those ideas have been around for a while, and I think you can make them work in this particular setup because it simplifies the general story in a way that more or less boils down to questions in K-theory de Rham cohomology plus compatibility, and those questions can be answered separately, and the question is, can the compatibility be answered? I guess one thing to say is I do have Euler classes constructed. Euler classes are very close to Tom classes. Tom classes, the trivial bundle, give you those suspension classes. So that's that last step of going from Euler to Tom classes that's missing. And that's the step I think I know how to do, but haven't worked out the details.
Thanks.
Structure of field theory, right?
I'd have to think about that. I think the setup here is a little bit different than yours, and some of the formal things aren't quite as nice. For example, field theories don't form a sheaf.
Oh, so this true one EFT with a small e is not a sheaf?
That is, so yeah, okay. we should talk about it. It depends on exactly which version of these things you want and where you want to map out of. But yeah, for that one, it is a sheaf. That's true. So maybe it works there automatically. You're right.
Oh yeah. So what is the shape of the sheaf actually?
Yeah, so this is where I think you'll end up with a sequence of spaces that are the correct spaces to get the cohomology theory, but you don't have the connecting homomorphisms automatically. That's the problem.
I see. Can we refine this to differential cohomology actually?
Yeah, that's actually not so hard, but well, I think it's not so hard. That's another one where I haven't written down the details. For K-theory, I know how to do it, so without like the one-dimensional version, I know how to do the differential story, and I think that basically just upgrades to this, but I haven't done that yet.
I see.
Very good. Yeah.
So at some point you require the manifold to be string manifold.
Yes.
So in how far does the maps you construct depend on the choice of a string structure?
So there's two manifolds involved. One is the parameter family, which is X. That's just a bare smooth manifold,
Right.
no assumptions. It's only when you're talking about constructing these classes from the string orientation, where did that go? Here, that you need a string structure. But notice this is an M here and a point there. And then in the example, in this example, the string structure is K, and up to deformation, it's K mod 24 that matters. So the string structure mattered in determining the underlying field theory, the deformation class.
And this a little bit more. Is the sigma of M, how does that depend on the string structure?
Yeah, so there's two primary pieces of data that show up in sigma of M. One is this representation of cylinders, some L0 and L0 bar and G0 bar. The string structure shows up there. And the second is, basically it shows up there in terms of modifying a connection to a super connection in some way. And then the other piece of data is some function on some moduli space of supertori. The string structure also shows up there. And then the final piece of data is you have to build some homotopy, and the homotopy is built out of these two choices. It's the same choice of string structure, and you don't get a homotopy unless they're the same.
Okay, but for example, the result in this pi n of KOFM, that also depends on the string structure.
So the invariance of the string structure will be here. This doesn't depend on.
Does not depend.
Does not depend, no. Yeah, so it's all coming down, like pi n of TMF lives in the middle here, and it factors through that, right? So you can interpret, one way of answering your question that's not terribly insightful in terms of the calculations, but is true, is that the degree to which this depends on the string structure is exactly like some shadow of how the class in TMF depended on the string structure.
Okay, any other questions? Okay, if not, let's thank Dan again for the very nice talk. Thank you, Dan.